Hi guys, in this video we're going to revise acids, bases and buffers through past paper questions, and this past paper question topic pack can be found in a link in the description below. This video is suitable for second year A-level students. So the first question, 20 centimeters cubed of 0.1 molar hydrochloric acid is added to 10 centimeters cubed of 0.1 molar sodium hydroxide. What is the pH of the resulting mixture? So the first thing we have to do here is work out the moles of the acid and the moles of the sodium hydroxide. Then we can see that the hydrochloric acid is in excess because the moles of this is greater than that of the sodium hydroxide. So we want to subtract these moles and we want to find out the amount of HCl that's left after reacting. This is a 1-to-1 ratio if you were to write the balanced equation for this. Next we're going to use the total volume, so 20 plus 10, 30 centimeters cubed, and work out the concentration of HCl, so that's the remaining acid after reaction, in the new total volume. And we come out with 0.033. That's our hydrogen ion concentration. And then to get pH, we can minus log this value to get 1.48. Next question is asking which of these four pairs is a conjugate acid-base pair. So you need to know that a conjugate acid-base pair differ by H+. So none of these are conjugate acid-base pairs, but these are. So you can see that these are linked. These differ by H+, H3O+ and H2O, one hydrogen difference. The next question is about weak acids. We have a pKa that's kind of similar to pH and it's used for weak acids. So the first thing we're going to do in order to find pH is work out the Ka of this. And pK and Ka have the same relationship that pH and hydrogen ion concentration do. So to get Ka, we do 10 to the minus pKa. And on the calculator, it looks like this. Shift, log, minus, and then minus the pK value, which is 4.76. Now we can use the Ka value that we just worked out, the concentration of the acid, Ha is just a general acid, to work out the hydrogen ion concentration. So we're going to use this expression, H plus equals the square root of Ka times by the concentration of the acid, to get our hydrogen ion concentration. After we've got that, we can work out pH by minus logging that hydrogen ion concentration to get 2.53. This next question is about weak acids and we have some Ka values, and it's asking us to find the pH of this concentration of propanoic acid. So we have to find the correct acid and its Ka value from the table, and it's that same expression again. To get pH of a weak acid, we use Ka times by the concentration of the acid and square root this. After we've got that, the hydrogen ion concentration, we minus log it. We put it into the pH equation that we use for strong acids. So with weak acids, there's just an extra step. In part B, we're mixing together an alkali and a weak acid. So we've got a strong base and a weak acid. And it says, show by calculation that 20 centimeters cubed of sodium hydroxide is required to reach the end point. So the first thing we're going to do is calculate moles of the propanoic acid, doing concentration times volume. Then I did the balanced equation so we can see it's a 1-to-1 ratio of the alkali to the acid. So the moles of sodium hydroxide should equal the moles of the acid, and then we can rearrange to find volume of sodium hydroxide by doing moles that we've just worked out over the concentration of the sodium hydroxide. It comes out in decimeters cubed and we just times by 1,000 to get it in centimeters cubed. Then this one's still the same question, part 2. Calculate the pH of the final solution. So the sodium hydroxide is in excess. That means we need to do the moles of the sodium hydroxide minus the moles of the acid. To get moles of sodium hydroxide, we do concentration times volume, and this information is on the previous page. We get this amount of moles. Then to work out the excess sodium hydroxide, we do the moles of sodium hydroxide minus the moles of the acid to get the moles of sodium hydroxide remaining. Then we can work out the concentration of hydroxide ions doing moles that we've just worked out over the volume. So the total volume is 70 because 45 plus 25. And here it's converted into decimeters cubed. After we've got our concentration of hydroxide ions, we can use Kw, and Kw is used for strong bases. So on your data sheet, Kw equals hydrogen ion concentration times by hydroxide ion concentration, and it equals this value, this constant. We rearrange it for H+, Kw over the concentration of hydroxide ions we just worked out. We get a value for hydrogen ion concentration, and then we minus log it, and we get a pH of 12.55. This next question is about ethanoic acid, a weak acid, and it gives us its Ka value. We also have a measured pH, and it's asking us for the concentration of the ethanoic acid to 3 significant figures. So since we're given a pH value, we can work out the hydrogen ion concentration doing shift log minus, and then put that pH value in, 2.44, and we get this for the hydrogen ion concentration. Then we can use the expression HA equals hydrogen ion squared over the Ka value. So it's that same expression that we saw on the previous pages, just rearranged for the concentration of the acid. And we get 0.754 to 3 significant figures. In part B, we're adding ethanoic acid to another weak acid, fluoroethanoic, and we have the Ka value of this one as well. An equilibrium is set up containing 2 acid-base pairs. Complete the equilibrium, label the conjugate acid-base pairs. So here we have 2 acids, and how do we decide which one donates its proton and which one doesn't? We can't just guess, so we have to use the Ka values. We have this one for the fluoroethanoic, and we have this one up here for the ethanoic acid. So we can see that the fluoroethanoic acid has a larger Ka value. That means that the fluoroethanoic is a stronger acid and is more likely to donate its proton. So on the right hand side of this equation, we're going to write the fluoroethanoic acid without its acidic proton, and it's donated that proton to the ethanoic acid, which is here. So we do the CH3 with an extra proton from here and a positive charge. And then our acid-base pairs are linked by H+. This next question is about buffer solutions. A student wants to prepare a buffer solution with a pH of 4.5. The buffer solution consists of a weak acid and its salt. The student wants to add 9.08 grams of the salt to 250 centimeters cubed of 0.8 molar of the acid. Show by calculation whether the student's experimental method would produce the required pH. So the best place to start is to work out the moles of the ethanoic acid, because we've got a concentration and a volume for this. Next we can work out the moles of the salt using mass over mR. So we've got the formula, we've got access to a periodic table, we can work out the molar mass of this, and we get these amount of moles for the acid and its salt. Now the moles of the salt is equal to this conjugate base, so we can use this expression which we use for buffers. H plus equals Ka times HA over A minus, and these are concentrations of the acid and its conjugate base. And we do have moles, not concentrations, but it's a ratio, so it doesn't really matter. Plug those in and we get this value for hydrogen ion concentration, minus log this, and we come out with a pH of 4.5, which is sensible. The next part says when the student prepares the buffer solution, the volume of the solution increases slightly. Suggest whether the pH of the buffer solution would remain the same, greater than or less than your calculated value in the previous question, and explain why. So if the volume of the solution increases, the ratio of the concentration of the acid to the conjugate base is still the same, and it's that ratio that's important, and because of that the pH will still be the same. The next one is about weak acids, but really it's a redox question. A student adds magnesium to an aqueous solution of ethanoic acid and a redox reaction takes place. Write the overall equation for this reaction and explain in terms of oxidation numbers which element has been oxidized and which has been reduced. So here's the balanced equation. This forms a 1 negative ion, so 1 minus ion, whereas magnesium forms a 2 plus ion, therefore we need 2 of this CH3 to balance. So metal and acid give salt and hydrogen. And then what's been oxidized? Magnesium over here is an element in its standard state, so it has an oxidation number of 0. Over here in a compound, it's plus 2. So magnesium's been oxidized, it's lost 2 electrons and it's gone from 0 to plus 2. Whereas hydrogen has gone from plus 1, each hydrogen is plus 1 in this acid, to 0 over here, where it's in its elemental form, its standard state. So that's been reduced and gained 1 electron. The next question is about conjugate acid-base pairs. We've got some Ka values and we need to remember that a larger Ka means a stronger acid, so that acid will be the one that donates its proton. This one, methanoic acid, is the stronger acid out of the two. So this one's going to lose its proton and donate it to this. So we do its conjugate base over here, and they're linked, acid 1, base 1. It donates that proton to the ethanoic acid, put the extra H here and a positive charge, and this is our acid 2 and base 2, so conjugate acid and base. So these are the two conjugate acid base pairs. Then part C, this links to the previous question. Use table 18.1 to answer the following questions. So that's the table with the Ka values of those two acids. The student measures the pH of ethanoic acid as 2.72. Show that the concentration of the ethanoic acid is 0.204. So we've got the pH. First thing we do is get the hydrogen ion concentration from this. After we've got that, we can plug it into this equation for weak acids. So I've rearranged for what we want to find, the concentration of the acid, and that's equal to H plus squared over the Ka value, which we got from that table on the previous page, 1.78 times 10 to the minus 5. And we come out with 0.204. Following questions about buffers. A student plans to make a buffer solution of pH 4 from a mixture of ethanoic acid and its salt. The student mixes 400 of 0.204 ethanoic acid with 600 of its salt. Calculate the concentration of the salt needed to prepare this buffer solution of pH 4. So the first thing we need to do again is to work out the hydrogen ion concentration of the buffer using the pH value that we want our buffer to be. So that comes out as 1 times 10 to the minus 4 in standard form. Then we can work out the moles of ethanoic acid doing concentration times volume. Remember to convert your volume into decimeters cubed. And we get this value for moles. Now we're ready to work out the concentration of the salt. So this is the expression that we use for buffers. And we want to rearrange it for the salt, which is A minus the conjugate base. So we plug in our Ka value and we do the concentration of the acid that we've just worked out over the hydrogen ion concentration, and we come out with a concentration for our salt. But this concentration here is in the 1 decimeters cubed or 1,000 centimeters cubed of the buffer. We want to find the concentration of the salt in the original 600, because we want to know what concentration we need when we're getting this 600 of the salt. So to do that, we're going to do the concentration that we just worked out over the volume, the original 600, and we come out with 0.024. So this next question is about a titration, and it wants us to draw a pH curve for the titration of a strong base against a weak acid. Now it tells us the volume needed of the weak acid, 25 of 0.08. So normally we do our straightish line, horizontalish line across to 25, and then an almost vertical line at the equivalence point. But if we look at the concentrations, the weak acid concentration is slightly lower than that of the strong base. So that means our equivalence point will shift slightly to the left, because less of this weak acid will be needed for neutralization by this strong base. So here we've got what's called the buffer region, where the pH is not changing very much at all. Then we've got a rapid pH change, and the equivalence point, the point at which equal amounts of acid and alkali have reacted, that is the middle of this verticalish section, and then it levels off again. So since it's a reaction between a weak acid, we're going to start pH around pH 3, 3.5, and strong base, we're going to finish anywhere in the region from pH 12 to 14. And the line has to carry on all the way to the end because we're adding 45 of the sodium hydroxide to the weak acid. Next it says the student considers using 4 indicators for the titration, and we have to pick which would be the most suitable. So to do that, we want to look at where our equivalence point is, so the middle of this vertical line, so around here-ish. And that's about pH 9, 8.5, 9-ish. And we want a pH range, an indicator with a pH range that falls within that. So Cresol purple is the best one. So Cresol purple because the pH range of the indicator matches the vertical section of the pH curve. So this next question, it says the student repeats the experiment starting with 25 of 0.08 molar HCN. So same volume, same concentration, but different acid, and add in the same volume and same concentration of the strong base. Predict one similarity and one difference in the pH curve using table 20.1. So that's down here, and that table gives us Ka values. So we can compare the acidity of the propanoic acid in that first pH curve and the hydrocyanic acid, which is what we're using now. So we can see that HCN has a lot smaller Ka than propanoic acid. That means it's a much weaker acid, so it will have a higher pH. So a difference is that the HCN, the hydrocyanic acid, will have a higher starting pH, and a similarity is that the end point or the equivalence point will be the same, and that's because it's still a 1-to-1 ratio between the acid and the base. Next question, the student calculates the pH of 0.8 molar iodic acid. The student assumes that the equilibrium concentration of this acid is the same as the initial concentration. The student measures pH and finds that the measured pH is different from the calculated pH. Explain why. So that means the assumption must be incorrect, and these kinds of assumptions, the equilibrium being the same as the initial, that only applies to weak acids. So that suggests that HiO3, iodic acid, is not that much of a weak acid. So a property of weak acids is that they barely dissociate at all. The amount of H plus ions on the right hand side of the equilibrium is negligible in a weak acid, but this suggests that assumption does not apply to this acid, and that this acid must therefore dissociate into its ions to a significant extent. This question is about buffers and ratios. So healthy human blood needs to be maintained at a pH of 7.4 for the body to function normally. Carbonic acid is a weak acid which together with hydrogen carbonate ions acts as a buffer to maintain the pH of blood. The pK value for the dissociation of carbonic acid is 6.38. Explain in terms of equilibrium how the carbonic acid hydrogen carbonate mixture acts as a buffer in the control of blood pH, and calculate the ratio of these in healthy blood. So if we start with the calculation first, we're given a pK value. We can calculate the Ka and then we can plug it into this expression for buffers. So K equals 10 to the minus pKa, and we come out with a Ka value of 4.17 times 10 to the minus 7. We're also given a pH value for healthy human blood. Let's work out the hydrogen ion concentration of that. So we're going to do the same thing. 10 to the minus pH, it's the same relationship. And we get hydrogen ion concentration there. Now we can use this expression. This is the expression, the equation that we use when we want to work out ratios in buffer calculations like this. So Ka over H plus is equal to A minus over HA. We've got the Ka value and we've worked out H plus. So we do Ka over H plus and we get 10.48. Now that is a ratio that is 10.48 over 1, or we can say, round it up, 10.5 to 1. Now let's address this part of the question. Explain in terms of equilibrium how it acts as a buffer. So to answer this, we need to talk about what happens when acid is added and what happens when alkali is added, and which way the equilibrium shifts, and include equations in our answer. So when an acid is added, the conjugate base will react with it. In that case, it's HCO3 minus. And the addition of H plus from the added acid will cause the equilibrium to shift left. This is the equilibrium, so this is carbonic acid splitting into hydrogen ion and its conjugate base. So since the conjugate base will react with the added acid, it's doing this reaction, HCO3 minus plus the H plus that's been added from the extra acid is going to move the equilibrium this way to form more of the carbonic acid. So when the alkali is added, the carbonic acid will react with it, and addition of the alkali will cause the equilibrium to shift to the right, because this is what's happening. The carbonic acid reacts with the OH minus from the alkali and it's producing more of this HCO3 minus, the conjugate base. This is the final question, and there's quite a lot to look at on this one, so we'll take it step by step. It says we're preparing nitrous acid by reacting with N2O3 and water, and the nitrous acid is the only product. So the first thing I did was write a balanced equation for that. We're given a pK value of the nitrous acid, and it says the chemist is making up a buffer solution. So they've weighed a sample of N2O3, we've made up a solution of HNO2, nitrous acid, and we're adding sodium hydroxide to this acid. And it says explain why a buffer solution forms in step 2 and find the pH and the mass of N2O3 that was used in step 1. So I've written under the balanced equation that we want to find the mass of N2O3 and the volume and concentration of the nitrous acid. So the next thing I did was work out moles of the nitrous acid using concentration times volume, and we get 0.05 moles. Then we can work out the moles of N2O3 using our balanced equation. So it's a 1 to 2 ratio of N2O3 to the nitrous acid. So if we halve the moles of HNO2, that will give us the moles of this from the ratios. Next, we can use those moles that we got from the ratios in the balanced equation to work out the mass of N2O3. And we can do that by doing moles times molar mass, and we get 1.9 grams. If we look at the rest of the question, we've calculated the mass. Now we need to explain why a buffer forms in step 2. So step 2, we're adding sodium hydroxide to nitrous acid, and acid plus base gives salt and water. And buffers can be formed by partial neutralization of a weak acid, and that's why it forms. So a buffer is formed from partial neutralization of the HNO2, and buffers consist of a weak acid and its conjugate base. And we can give an example of what those are. Or we could have said NaNO2 there. And in a buffer solution, the weak acid must be in excess. So we can also prove that in order to get top marks. And I'll screenshot the mark scheme and put it in this video in a second. So we've got the moles of sodium hydroxide coming out as 0.015, doing concentration times volume. The moles of NO2 minus, that is just NaNO2, so it's a 1-to-1 ratio, they will be the same. And the moles of acid remaining after it's reacted, so what's left of the acid after it's reacted with the sodium hydroxide, we want to prove that it's in excess, there's still some there. So we take the moles of the acid that we worked out at the start, minus the moles of the sodium hydroxide, and this is how much we've got left in excess. Thought we'd finish, but we still need to find the pH of the buffer solution. So to do that, we need to find the Ka value from the pK given in the question. It says we have a pK of 3.34. So we can do the inverse log of that. The total volume is 1 decimeter cubed. That means the moles are equal to the concentrations. Rearrange this expression used for buffer calculations in terms of H+. So H+ equals Ka times Ha over A minus. We come out with our hydrogen ion concentration and we minus log it and get a pH of 2.97.